Good evening. I should like to begin with something that troubles me, has troubled me for many years. If you glance at the clock above the door, you will see its minute hand advance, never retreat. Smoke rises, disperses, and does not gather itself back into a tidy ribbon. And I am, let us be honest, older today than I was yesterday, and tomorrow I shall be older still. This direction, this arrow, as some call it, feels absolute. And yet, when I sit at my desk and write the equations we use to describe nature, Maxwell's laws of electromagnetism, Newton's mechanics, and even the field equations of general relativity, I find something remarkable. These fundamental equations do not, by themselves, prefer a direction of time. Consider a simple wave equation. It contains time only through a second derivative. If I replace t with minus t, nothing changes. The equation remains true. The mathematics permits the wave to run forward or backward in time with equal legitimacy. The same symmetry appears in idealized mechanics and in the classical laws we most often regard as fundamental. So we arrive at a puzzle. The laws whisper, forward and backward are equivalent, but experience shouts, forward is the only direction. Which is correct? I believe both are correct, but they speak about different levels of description. To see this, we must look not only at the grand equations, but at what it means for a system to be in one state rather than another. First, the reversibility puzzle. Let me demonstrate. I pick up a piece of chalk. If I drop it, it falls. Now imagine we filmed the event and played the film backward. You would see the chalk leap upward into my hand. Would that violate the laws of mechanics? Not at all. If the chalk had precisely the right upward velocity and the air offered no dissipative resistance, conservation of energy and momentum could be satisfied. The reversed motion is permitted. And yet, we never observe chalk spontaneously leaping upward from the floor. Or consider the planets. A world may orbit its star one way or the other. The gravitational equations do not object. The direction of motion is not forbidden by the law itself. At the microscopic level, collision by collision, many processes can occur in either temporal order without contradiction. So I ask, where does the asymmetry come from? Where does the arrow hide? Second, ice in tea. Imagine a cup of hot tea. Into it I place a cube of ice. What happens? The ice melts, the tea cools. Heat flows from the warmer tea into the colder ice, until both reach a common temperature. You have observed this 1,000 times. Now imagine the reverse. Begin with lukewarm tea and lukewarm water, and then spontaneously, one region becomes colder and crystallizes into ice, while another region becomes hotter. The drink separates itself into hot and cold without any outside intervention. We do not see this. But notice, I have not proposed that energy vanish or appear from nowhere. The molecules are the same molecules. If you inspect any single collision, any one exchange of kinetic energy, you cannot point to a microscopic law that forbids the reverse exchange. So why does it not happen? The answer is not that the reverse is impossible. It is that the reverse is so fantastically improbable that for all practical purposes it never occurs. And probability, this is the doorway through which the arrow of time enters physics. Third, the language of arrangements. When ice is solid, the water molecules occupy a comparatively constrained pattern. When it melts, the molecules roam freely. They can be arranged in enormously many more ways, while still looking, to our crude eyes, like liquid water. This leads us to a crucial idea: multiplicity. A macrostate is what you can describe with a few words: hot tea and ice, lukewarm tea, solid ice. A microstate is the exact microscopic arrangement, the precise positions and motions of every molecule. We ask, how many microstates correspond to the same macrostate? Let us call that number omega. For a highly constrained macrostate, omega is relatively small. For a spread out, mixed, equilibrated macrostate, omega is astronomically large. And here is the essential point. If the microscopic dynamics wander among microstates without bias, then the system will overwhelmingly tend to move from macrostates with small omega to macrostates with large omega, simply because there are so many more ways to be in the latter. This is the meaning behind what you call the second law of thermodynamics. It is not a mystical command. It is a statement of statistical inevitability. Boltzmann captured it in a single line: entropy equals k times the natural logarithm of omega. So the ice melts and stays melted because the melted macrostate corresponds to vastly more microstates than the frozen one. A refreezing would require the molecules to conspire into one of the rare special arrangements again, possible in principle, but unimaginably unlikely. Fourth, the great puzzle: why any order exists. If entropy tends to increase, if systems overwhelmingly drift toward larger omega, then why is there any low entropy in the universe at all? Look around this hall. The chairs are arranged. The air is not separated into perfect layers. The walls remain walls. And you, each of you are an extraordinary concentration of structure, cells, organs, and a brain full of delicate patterns we call memory and thought. If the universe were simply a system wandering long enough, why is it not already in equilibrium, uniform, featureless, exhausted? The best answer we have is this. The universe began in a very special state, an extraordinarily low entropy state. And I must add something that is often missed. With gravity, low entropy does not simply mean neat and clumped. In a gravitating universe, a smooth, nearly uniform distribution can represent a remarkably special condition, low gravitational entropy, while the later formation of stars and galaxies, though it looks like order to the eye, corresponds to an overall growth of entropy when the full accounting is done. So the puzzle of time's arrow becomes in part a cosmological puzzle. Why were the initial conditions of the universe so special? Fifth, the universe as a wound spring. Astronomers have gathered evidence that distant nebulae are receding, suggesting that the cosmos on the largest scales is expanding. If that is so, then extrapolating backward leads to an earlier state that was denser and hotter than the present. Some speak of a primeval atom, others of an initial fireball. The names matter less than the implication. The early universe appears to have been extraordinarily smooth and extraordinarily far from equilibrium in the gravitational sense. You may think of it as a spring held tightly wound. Everything since has been the unwinding. When a star shines, it converts concentrated nuclear potential into diffuse radiation. The starlight streams outward and is eventually degraded into low-temperature heat. Entropy increases. The spring relaxes. When a planet forms from a cloud of dust, it seems to create structure. And locally it does. But the formation releases heat to space. The surrounding environment gains entropy. The total, planet plus surroundings, moves toward higher entropy. We are living, so to speak, on an inheritance. The low entropy of the past is the source of the free energy that makes change possible today. Why the beginning was so special, I do not know. It is perhaps the deepest mystery here. We can trace the consequences, we can test the mathematics, but the ultimate reason for those initial conditions remains hidden. Sixth, life as entropy's sculpture. Now you may object. Living things become more organized. Does life not contradict the second law? A fine question. A seed becomes a tree. Locally, complexity and organization increase. But life is not a closed system. It lives by consuming free energy and exporting entropy. Where does a tree obtain its power? From sunlight. Energy arriving from a very hot source, the sun. The Earth then radiates roughly the same energy back to the cold of space, but at a much lower temperature, as infrared heat spread broadly in all directions. That degradation from hot, concentrated energy to cooler, more diffuse radiation produces an increase of entropy that more than pays for the local order the tree builds. The same is true for you. You eat organized molecules. Your body builds and repairs. Your mind thinks. But you also radiate heat, exhale waste products, and increase the entropy of your surroundings. Life does not defeat entropy. Life is one of the intricate ways entropy increases. Think of a whirlpool in a river. The whirlpool has form and persistence, but it exists only because water flows downhill. It is not a rebellion against the flow, it is a structure made possible by the flow. So it is with living beings, temporary eddies in the river of entropy. 7th, memory, choice, and causation. Why do you remember yesterday but not tomorrow? Memory is a kind of record. A record requires a physical trace: ink on paper, silver on a photographic plate, or changes in the chemistry and wiring of a brain. Creating such a trace requires that the recording device begin in a state with available free energy, capable of being reorganized, so that it can end in a state that encodes information. In other words, records are created by entropy-increasing processes. The correlations we call memories point toward the lower entropy past. This is why the past is full of evidence and the future is not. The future may be consistent with the laws, but it has not yet left traces in the present, because leaving traces is itself an entropic, one-directional process. And causation, our sense that we can influence what comes next, has the same root. We can act on the future because we still have stores of low entropy to spend. We can push systems from constrained states to less constrained states. But we cannot, in any ordinary circumstance, push the world from high entropy back into low entropy. Such reverses are not forbidden, but they are fantastically unlikely. So even the psychological arrow, memory, decision, anticipation, leans upon the thermodynamic arrow. 8th, the heat death and its meaning. If the universe continues toward equilibrium, then the gradients that power change, differences of temperature, chemical potential, and so on, will diminish. In the limit, there will be no free energy left to do work. Stars will not shine. Engines will not run. Complex structures will not be sustained. This general idea is sometimes called the heat death, not a dramatic explosion, but a gradual fading into a state where nothing of macroscopic interest can happen, because everything that could fall has already fallen. Whether the cosmos ends exactly in such a state depends on the detailed fate of expansion and gravity. But the underlying lesson remains: usable order is a resource and it is being spent. Finally, the privilege of this moment. We exist in a narrow window between an ordered past and a more disordered future, where differences still exist, where stars can burn, where planets can cool, where chemistry can run, where life can arise and mind can awaken. You are made of atoms forged in ancient stars. Your body is organized by patterns that trace back to conditions set long before any human history. And now, improbably, you are conscious, able to contemplate these truths. Yes, the chalk will crumble. The building will not stand forever. The sun itself will one day exhaust its fuel. The arrow does not reverse, but before it ends, it is. In German I would say, das genügt. That is enough. The arrow of time points one way, from fewer arrangements to more, from constraint to possibility, from a special beginning toward a more typical state. We cannot change that direction. But notice the gift hidden inside it. Without this one-way drift, there would be no change. Without change, no events. Without events, no story. So when I watch ice melt and not refreeze, when I watch smoke disperse, when I watch the chalk fall and remain fallen, I no longer find it merely troubling. I find it illuminating. It tells me where we are, riding a current that began in a rare, ordered condition and moves, step by step, toward equilibrium. The universe is vast, and we are small. But for this moment, this brief, improbable, precious moment, we are here, and we understand, at least partially, why. Thank you for your attention.